And actually, yeah. So what we're gonna do is just introduce you to chapter 31. So we're going back to chapter 31, the previous chapter, because to me it just seems to make more sense to deal with light at the same time when we're going to start optics. But it's sort of interesting that the stuff we've been talking about, right? Remember this experiment? What was this experiment called? Or what was this showing you? Where you have a current going across near a compass. What does that give you? Remember? It creates, so somehow moving charges, right? That's what current is, creates magnetic field, right? And then in chapter 30, I also show you this, where we have a magnet, and if we move it around, right, a changing magnetic field gives you either, gives you current, EMF, or electric field, right, somehow. So somehow, intrinsically, right, either electric field changing creates magnetic field changing gives you electric field. So those two fields are actually intrinsically connected to each other, and when you combine those two together, what happens is that you get light. And it's actually sort of a really weird, or either it makes a lot of sense or it makes no sense. Because somehow, right, light is actually able to propagate itself in a vacuum, meaning that it doesn't need anything to propagate. So, for example, like water wave, right? It needs water for it to oscillate up and down, right? Where light does not need anything. And I'm just gonna give you guys a little conundrum here to start with, to tease you guys into maybe reading the textbook and figuring this out, okay? So far we've been talking about electric field and B field kind of separately from each other. And we're gonna see how we're gonna get into a little of a paradoxical situation, okay? If I describe the situation to you, okay? We have two people, Alec and Brittany, and the reason we picked those names is because one starts with an A, the other one starts with a B. They happen to live in the same universe, okay? That's a gift, hopefully that's not too far leap, okay? Okay? Brittany happens to be holding a charge and jogging while Alec is just standing still and just, hanging out, okay? So what I'm gonna do is I'm gonna draw Alec with an A, right, standing still, and then Brittany with a B, right? She's the one holding a charge with some charge Q, and she's jogging, in some direction with some velocity V. Okay. The question I want to ask you guys, right? Is there a magnetic field in this situation? How many of you guys think there is a magnetic field? Okay. Most of you guys? Okay. How many of you guys say there's no magnetic field? And I'm just being tricky. Right? You voted for both. Okay, so I am being tricky, right? So in this case, there should be a magnetic field, right? Because there's a charge that's moving, right? We know that, in order to calculate magnetic field, right, it's basically whatever the charge is, velocity cross producted with like r hat over r squared, this complicated formula thing, right? So there is some, as long as you have a charge that's moving, there should be some sort of magnetic field. Okay? So here's the conundrum. Little wrench I'm gonna throw at you. Well, let's examine the system from Brittany's perspective. Meaning, right, instead of Alec looking at Brittany running along at some velocity v, well, what if we just put our little go cam on Brittany's head and think about from her perspective, what does thing look like? Okay, so from her perspective, right, she is not moving, right, because she's always in her place, right? So in that case, right, Brittany is still holding a charge, right, but in her frame of reference, right, she's not moving. Alec is the one that's actually moving, but going backward, right? So if I'm running from my perspective, you're actually moving in the opposite direction, right? Does that make sense? So now I'm going to give you this case once again, right, where the charge is not moving, right? Is there still a magnetic field? So how many of you guys think there is still a magnetic field? Okay. Okay. So 2, not as many as last time. How many of you guys think there is no magnetic field now? Just because we switched the perspective. Kayla. There's no magnetic field. In fact, Kayla is right. There is no magnetic field. So how does this happen, right? Why does the magnetic field depend on your point of view, right? So like if I'm in a lab, working on some device, there's a magnetic field here, but then Chad sitting back there say, oh, there's no magnetic field. What are you talking about, right? So this is a paradox, right? It's known as a paradox, and we're going to try to resolve this paradox hopefully next time. But before we go, since I still have about 3 minutes, okay? Well, we may not be able to figure out, this magnetic field situation, right? And you might think that, well, magnetic field is this thing that, physicists just made up, right? Right? Because it's not really like fundamental to things, right? Magnetic field is just a way for us to quantify how much force there would be applied to a charge that's actually moving in that magnetic field, right? Okay? So what if, we make, Brittany run in a constant magnetic field, right? So there is already a magnetic field in there. So I'm going to do is I'm going to draw a bunch of magnetic field, let's say, going into the board, right? Right? Imagine this universe has some constant magnetic field in it, right? And let's see if we can figure out whether or not there's going to be a force on that charge. Because if you have a charge moving in a magnetic field, there's going to be a force on it, right? It's going to start, if basically it's massless, right, it's going to start floating up, okay? Let's see what happens. So looking at this from Alec's point of view, okay, once again, Alec is just standing on the sidewalk, right? And Brittany is the one that's running with some charge Q that's, she's carrying in front of her for some reason, right? In that case, right, is there going to be a force, right? So once again, right, magnetic force can be calculated by just the charge V cross B, right? We're going to use our little right-hand situation again, right? Or we're going to count from 1, V is in this direction, B is into the board, so the magnetic force is actually going to be pulling it upward, okay? So what will happen is that as she's running along, that little charge is going to feel like it weighs less because there's some magnetic force trying to lift it up, right? So there's some levitation force, okay? And she should be able to sense that, right? It'll be, whatever charge you're holding, right? It'll be a little bit lighter just because I'm moving, right? Right? So, but what happened is that, right, if we go to Brittany's point of view, I'm going to erase this real quick, right? Okay, we're in the same universe though, right? XX, sorry, it's going to take me a lot of time to write this stuff, right? If we are in from, now we're going to switch our GoCam from Alec to Brittany, right? Where we're looking at this charge, right? And then Alec is the one that's moving backward the other way, right? She shouldn't sense a magnetic force, right? Because in her perspective, the charge is not moving, right? So that's the paradox I'm going to leave you guys with, okay? Okay, so that's the cliffhanger, okay? So how come there's a force from Alec's perspective, but there's no force from Brittany's perspective, right? Shouldn't the two be the same, right? If I throw an object at you, you're going to feel that force no matter which perspective you're feeling it, right? Okay, so and of course this is in the textbook, so it's not, like a, you don't have to wait the whole week to figure it out.